Okay, hello everyone. Welcome back to another Topos Institute Colloquium. Today we're very happy to have Alex Kavvos talking to us about two-dimensional Kripke semantics. So please, Alex, whenever you're ready.
Thank you very much, David. It's a great honor to be speaking at the Topos Institute Colloquium. This talk is about modal logic. It's about categorification. It's about dualities and how all these things fit together. Uh, Almost nothing in this talk is particularly original, but I hope the synthesis is new and at least has not been presented that way. It is based on two papers published at FSCD and MFPS last year, 2024, but this is very much still an ongoing program of research. By the way, for anyone listening, please feel free to unmute and interject, ask any questions at any time during your talk. Okay, so what is two-dimensional Kripke semantics about? Modal logic is a very important kind of logic in computer science. Some people call it intentional, people call it all sorts of things. Dana Scott wrote a lovely article called Advice on Modal Logic about 40 years ago, which is still worthwhile reading today. But in practice, it's about state change and about reasoning about state change. So, for example, there are temporal logics. These are kind of modal logics. There are epistemic logics. These have to do with knowledge. There are dynamic logics, which are about reasoning about state change after you run a program. And last but not least, there's a Hennessy-Milner logic. It's a logic of concurrent systems that exactly characterizes certain bisimulations. In almost all these cases, logics are given Kripke semantics. The Kripke semantics are usually very simple. There's a set of worlds, there's a relation between worlds, and W is related to V if from W you can somehow access V. But maybe in the last 20 years, 30 years, in particular in the last 10 years, I would say, there's been quite an awful lot of work on the Curry-Howard-Lambert correspondence of modal logic, which leads to what we could call modal type theories. And in type theory, proofs are important. So the semantics of a formula is not just whether it's true or not, but also the way that this formula is proven has some computational meaning. And these modalities, you could call them type theoretic, arise everywhere in programming. They can represent logical time, as they do in guarded recursion. They can represent proof irrelevance, as they do in homotopy type theory. They can stand for global sections, which Mike Schulman has used to prove synthetically a version of Brown's fixed point theorem. And they can also talk about information flow, about parts of programs that don't communicate with each other or where data can't flow from one region of a program to another. For many years, I've worked on these type theoretic modalities and wondered, how do you connect these to Kripke semantics? And this is what this talk is about. So we start from a very abstract perspective, and we try to make it as concrete as possible and use things that are fairly well known to category theorists. So I'll go a little bit faster than usual in this talk, which has been written with a logical audience in mind, but please stop me if anything seems unclear. Okay. So a lot of category theory arises from duality, and a lot of interesting categorical results, where you usually have some category of spaces, and if you op that category, you suddenly can see category of algebras. If you look at intuitionistic logic, let's start with something very simple, intuitionistic logic, you can have a Kripke semantics for that. That was discovered by Kripke through a translation through modal logic in the 60s, but you can ultimately just write it by itself. And the idea is that you have a poset. So it looks a little bit like a space, worlds, and an order between them, which increases information. That's the most specific semantics of intuitionistic logic. The most general semantics, you could say, is Heyting algebras, where a simple way to make one is to take the formulas of intuitionistic logic and just do a big quotient up to equivalence, and then you find a particular kind of algebra. In particular, it has finite meets, finite joints, and right-hand joints for the and C functor. In this diagram, you can see four quadrants. On the left, I've got spaces. On the right, I've got algebras. On the first line, I've got what the situation looks like when you have just orders. So an order theoretical treatment of logic, no proofs. The bottom line is what you get when you add proofs and you move from an order theoretic setting to category theoretic setting. So if we have a Kripke semantics, one of the things that is known, but I will show you again, is that you can construct a Heyting algebra. So that's an instance of the most specific semantics, yielding an instance of the most general one. We can add proofs to Heyting algebras, and we obtain something called a Cartesian closed category. And the question is, what goes in the other quadrant? Now, you could call that a two-dimensional Kripke semantics over, well, before we had just a poset, now we've got a category. We can think of a category as a poset with proofs. So every judgment that W is less than V comes with a proof of this piece of information increase. And indeed, the construction that we see at the order theoretic level is just the preshift construction, which if you take a category and you take the category of preshifts over it, you get a Cartesian closed category. Now, so far so good. This is folklore and is well known. But if you try to do it for modal logic, it seems to be a lot more complicated. In particular, it's not obvious how to fill any of these four quadrants of space versus algebra, orders versus categories. In 2018, Ranald Clouston wrote a paper where he provided an answer, at least in the case of the algebraic treatment and also categorical, so with proofs being represented. And the answer he gave that would be a Cartesian closed category, or even bi-Cartesian, with an adjunction on it. Now, at the time, I must say I did not think that this was the correct solution, but time and time again, I've been proven wrong. Over the last 10 years, we've developed a number of type theories based on this adjunction formulation, which work extremely well. And they work so well that they can go up to the multimodal level. They extend to dependent type theory, and they do all sorts of other interesting things. Now, if you look at the proof theoretic structure of that, I will have no syntax in this talk. It's a category theory colloquium. But if you do look at the syntax, it looks a lot, in fact, it's just isomorphic to what people call Fitch-style natural deduction. And this pattern has proved remarkably robust. Because this is completely category theoretic, you've got everything up to equivalence. This is what Lauvier would call an objective answer to the question. Okay, so let's try and fill the other four quadrants. If I decategorify this, I get a Heiting algebra with a Galois connection. Okay, easy, well known, no surprises there. What's perhaps less known, but would be known to experts, is that this is exactly induced by a Kripke semantics over a poset. Remember, that's what we had in the intuitionistic logic case before. But now we also have what we call a bimodule over this poset. I'll explain what that is in a minute.
Alex, I think Steve's trying to say something.
Yeah.
Can I interrupt with a clarification?
Absolutely.
Is the adjunction an endomorphism, or is it a monad, an adjunction to another category?
It's an endomorphism. It's just any old CCC with an adjunction on it.
An endo adjunction.
Endo adjunction, yeah.
Thank you.
So for set, of course, these would just be times A and A implication. So there's no other adjunctions to set. But on preshift categories, there's a lot more. Thank you. Okay, so if we now recategorify that, we get that the spatial version is what we call a two-dimensional Kripke semantics. And for that, you require just two things: any old small category with a profunctor, endo profunctor on it, which is, you could call the categorical version of what it means to have a relation, in particular, a relation over a category or a relation that's compatible with a category. So the roadmap, I'll sort of try to piece together a bunch of things. If you look at the original paper on this, it has 107 references. I read everything I could on this topic, and I'm sure I've missed a few things, but I've tried to be as exhaustive as possible. I'll first talk a little bit about how this picture works for intuitionistic logic. Then I will introduce bimodules, and then I will show you what you can do with this extra perspective, introducing something I call the stable semantics. Okay, so space versus algebra for intuitionistic logic. Here's a brief reminder of what the Kripke semantics of intuitionistic logic look like. Start with any old partial order. We call that a Kripke frame. It's just a set of worlds and a partial order on them: reflexive, antisymmetric, transitive. Now suppose that for each variable of our logic, for each proposition, we assign an upper set. So an upper set is a subset of the worlds which is closed under the relation but upwards. So if W is in S and W can increase to V, then V is also in S. The meaning of this is that in intuitionistic logic, we have no belief or knowledge revision. If we learn that a proposition is true and our information increases, then the proposition remains true. So every time we interpret a proposition, it should be interpreted by an upper set. And then we define a relation between worlds and propositions. I don't know if you can see my highlighting. I hope you can. Pardon. And when does the word W force a proposition? Exactly when W is in the V of P, the upper set that interprets P. When does W force negation or falsity? Never. When does W force a conjunction? Exactly when it forces each of its conjuncts. Same with a disjunction. And the most interesting clause is the one for implication, which is that W forces an implication if the following happens. For any possible increase of information, so for any V that I can reach from W, if at that V, phi, the antecedent, becomes true, then so should the consequent psi. If you look at this definition, you can prove a very quick lemma, which says that if W forces phi, and I can increase my information from W to V, so W is less than V, then V also forces phi. So formulae that become true remain true. And Kripke proved that a formula is valid in all frames and all of their worlds, exactly if it is a theorem of intuitionistic logic. So this semantics is really nice. It's the most specific semantics of intuitionistic logic. And you can use it really easily to prove that things don't hold. It's fantastic for teaching undergraduates, because if you say, well, P or not P, how do I prove that this doesn't hold? You find a Kripke frame in which it doesn't, and it's very easy to find one. Quick recap, although I'm sure nobody needs it here, of the most general semantics. A Heiting algebra is a lattice, has finite meets and joins, such that for every two elements x and y of this lattice H, there exists an x arrow y, the exponential of x and y, such that this adjunction property holds. So if C and x implies y, then C implies the implication, the exponential of x and y. If you squint at this, it's just the introduction rule for implication or the abstraction rule for the lambda calculus. Okay, how does this work? We can interpret, if we know how to interpret each proposition, then we can interpret each formula. And how do we do that? Just inductively. We translate and to meets or to joins, an implication to these exponentials. And it's very easy to prove by the so-called Lindenbaum-Tarski construction that a formula is valid, which is to say it's equal to 1, the top element, in all algebras, exactly if it is a theorem of intuitionistic logic. Okay, hopefully there are no questions on this, but please speak up if there are. So here's a quick sketch of the construction that takes you from Kripke semantics to Heiting algebras. Start with a Kripke frame, W and an order, and take this particular Heiting algebra, in fact, complete lattice, 2, which has two elements, 0 and 1, with 0 being less than 1. Now, if we look at the set of monotone maps from W into 2, we find that it has many curious properties. First of all, it's exactly isomorphic to the upper sets of W. If you write down monotonicity for these maps, they are exactly the idea that if something becomes true and the order increases, then that thing should remain true. By true meaning we map it to 1. Second, it's a complete Heiting algebra. So a frame or a locale, depending on how you wish to view them. You have arbitrary joins and meets. Fact number 3, there's an embedding, the principal upper set embedding, which goes from the op of W into these upper sets. And I've written in terms of upper sets here, but you can write it equally well in terms of monotone maps. It takes W to all the worlds above it, the set of worlds above it. And it's very easy to see that this is actually an upper set. And this embedding preserves meets and exponentials. The most interesting bit here, and the key bit, is that an element is prime in a complete lattice, which is to say that if it's below a least upper bound, then it must be below one of the elements that are being least upper bounded. So if P is less than least upper bound, there exists an I such that P is less than DI, exactly if it is in the image of this principal upper set embedding. So in particular, when we look at this set, at this order, in fact, we can recognize the principal elements exactly by this primality condition without saying, well, they are the things in the image of the map. We can just see them. And finally, the most important property is that every upper set S in here is exactly the join of primes below it. So S is equal to the least upper bound of all the prime P's contained in S. Oh, and I did tell you that the primes are exactly of this form. So you take all the W's in S, you take the principal upper set of W, and you stick them all together, and lo and behold, you get back S. In short, you can say that W2 is a prime algebraic lattice, and these have been very important in the work of Glyn Winskell on event structures and other things, in particular in the guise of prime algebraic domains, which are a more specific structure. You can sum up this entire discussion by saying that you've got a duality. So if you look at the category of posets and you take its op, then you get exactly the category of prime algebraic lattices. So these are exactly lattices of this form. They are complete Heiting algebras, and everything is the join of primes below them. And the morphisms are complete. They're complete morphisms. They must preserve all meets and joins. This has been discovered. This was discovered by Rainey in a 1952 paper, but then rediscovered by Nilsson, Plotkin, and Winskell on the first paper on event structures. Okay, so we kind of see the structure that arises here. We see that from Kripke semantics, if you take upper sets, you end up in Heiting algebras. Now I'm going to categorify this full discussion and hopefully obtain some proofs. And indeed, the upper sets will now be replaced by taking pre-sheaves. For this, we have to think of a small category in a slightly different way than we normally do. We normally think of a category as, well, not always, but a lot of the time, we think of a category as a collection of mathematical objects and structure-preserving morphisms. No, in this particular case, we'll think of a category as having objects and morphisms being proofs that something is less than something else. So the objects are now the worlds. So before we had reflexivity in our partial order, now we have an identity morphism, which proves that X is less than itself. Before we had transitivity. If we had that X is less than Y and Y is less than Z, then X would be less than Z. Now we don't just have that. If we have two proofs that X is less than Y and G and Y is less than Z, respectively F and G, then we have a composite morphism, which proves that X is less than Z. So a category in this guise is just the partial order that carries proofs with it. And of course, we need the usual axioms to make sure that these proofs are coherent. So composition is associative, and the identity element is truly an identity element. So we can look at a category, a very small category, as a space with some kind of direction, with points and paths between them, but directed paths, things that can't be inverted. And then we can very easily define what we could call a two-dimensional Kripke semantics. This is just an illustration. It's not meant for correctness. But we can define a set, given a formula phi, we can define a set of proofs that phi is true at the object or world W. And we can do this as we did before by induction of phi. When is false true? Never. There are no proofs of false. When is a conjunction true? Exactly when I have a proof of its first conjunct in the same world and a proof of the second conjunct in the same world. When is a disjunction true? Exactly when I have a proof coming from one of those two sets. We need some additional tagging here to remember where this proof came from. Is it a proof of phi or is it a proof of psi? And finally, I've written it in type theoretic notation, and also it's not correct, but I've written it for illustration. When do we have a proof of an implication at world W? Well, exactly when, for any world V and any increase of information, proof of increase of information from W to V, then I have a function that takes proofs of phi at V to proofs of psi at V. This is, of course, not exact because you also need a naturality condition that I've not written here, but you can write it fairly easily, especially with this type theoretic notation. Now, remember, before we had monotonicity. Now this becomes a slightly different thing because it must be tracked by proofs. So if I've got a proof of phi at W, and the proof is X, and I have a proof that information increases from W to V, or just a way of increasing information from W to V, then I can define F acting on X, which is then a proof that phi is true at V. And if I collect all these proofs together and everything fits nicely, I get what we call a pre-sheaf, or a functor from C into Z. So every formula is now associated with a pre-sheaf, and the pre-sheaf gives you at each world the set of proofs that the formula holds at that world. And the action on these formulas is exactly monotonicity. This is the same slide as before with the, well, zero-dimensional Kripke semantics, but if you go back and forth, you can see that they look exactly the same. The only addition is proofs. Okay, all of this is now basically folklore, and we can play the same trick of constructing pre-sheaves as before. The only difference is we replace the little poset 2 by the category of sets. That's a classic move by Lorvier. I have a reference there to a 1973 paper where this is done beautifully, but one must be a bit careful because there's a bit of an asymmetry here, at least in the meta theory. Whereas 2 only gave you that something is true or false, set is lopsided. It represents falsity in one way, the empty set. So a formula that's not true at a world has no proofs. But if a formula is true, it can have a lot of proofs in that set. So there can be a lot of proofs that a formula is true. So intuitionistic logic has this thing. It's this negative fragment. If you use negation, all computational content is erased, all proof theoretic content is erased. But we can still see the construction as before. So this category C to set, the category of pre-sheaves, is a co-complete and complete Cartesian closed category. The principal upper set embedding is now, of course, known as the Yoneda embedding. And I'm using the covariant one because I work with covariant pre-sheaves in this work. And that can be seen to preserve products and exponentials. Remember that certain sets, upper sets, were prime. This is now replaced by the notion of being tiny. So pre-sheaf P is tiny if the morphisms out of it, that functor preserves colimits. And in fact, all representable pre-sheaves, so things in the image of this embedding, are tiny. And actually, if C is Cauchy complete, so if all its idempotents split, then we get the converse. We get that, in fact, all tiny objects are representables. So now we have some extra structural proofs, and we start to see small differences compared to the traditional order theoretic picture. Finally, this is something known as the co-Yoneda lemma. Every pre-sheaf can be written as a co-limit of tiny objects. So I take the elements of the pre-sheaf and I take a big co-limit over that diagram. And for each one of these elements, I stick a representable. And if you look at the previous slide, which I should have immediately afterwards, it's exactly the same fact that every upper set is the join of primes below it. So the join is the co-limit, and the principal upper sets are just the representables. And this leads to kind of two duality, which is due to Marta Bungay, and you can find in her thesis from 1966, which is that if you take the category of Cauchy complete categories and you op it, you get the category of all pre-sheaf categories. And in fact, there are ways to recognize these as the complete and co-complete categories, and they have a strong set of generators that you can write everything in terms of. And that's exactly what you have in a prime algebraic lattice. Every upper set is a join of primes below it. So we categorify that image and we get pre-sheaves. All of these results were known by 66, which I think is just wonderful. So this two duality shows us that we have a correspondence between Cauchy complete small categories. You can think of these as two-dimensional Kripke frames, and pre-sheaf categories, which you can think of as proof-relevant prime algebraic lattices. So you can define two-dimensional Kripke semantics to be just a categorical semantics in the usual sense of lambda calculus in a pre-sheaf category over some small category C. Okay, that's the picture so far for intuitionistic logic. I'm happy to take any questions if anyone has any. Okay, if not, then I will proceed to adding the modalities. So because we work with proofs, we have to be intuitionistic for known reasons. The question is, what is intuitionistic modal logic? And that has not been cut and dried, at least not quite as much as the part of the image I've presented so far. In particular, most modal logic comes with two modalities, a box and a diamond. You can see them down here. And while the box is really well behaved categorically, it's not clear what the diamond should be. Normally, what you have in a modal logic is you have some set of worlds and an accessibility relation, and you define box and diamond in terms of those. But since we also have this additional intuitionistic dimension, we have an order on W. And this relation must somehow be compatible with the order. And it's not exactly how to do that. It's not exactly clear how to do that. So Alex Simpson, in his thesis, defined a set of criteria, which I've reproduced here, on what should be an intuitionistic modal logic. I've written these just for reference. I'm going to ignore all of these, and I'm going to try and complete the alternative proposal, which is to look at just textbook category theory and see what that tells me. So to explain that, I first have to talk a little bit about extensions, Khan extensions in particular left Khan extensions along the Unada embedding. So I'm going to quickly rush through this because I suppose it will be known to most of the audience. Suppose W prime is a complete lattice, and let F be any monotone function between these two posits. Remember, W prime must be complete. So this function is diagonally here. This is the embedding of W into the upper sets, so just the Unada. It is well known that there is a unique way to lift this F to an F lower shriek, which preserves all joins and makes this triangle commute, actually strictly. And how do you define that? This is how you can write it out, at least in the order theoretic setting. You take an upper set, S, you apply F to each one of its elements, and then you take a big least upper bound. And this big least upper bound is why you need W prime to be complete, so that you can take it. Now, because this preserves all joins, by the adjoint functor theorem, it has a right adjoint, which is this F upper star. And you can write this rather clearly. You can say that it maps little w prime to the set of w's such that if you apply F, you end up below w prime. And then you can prove the adjunction property where the order up here is inclusion, as it is with upper sets, and the order down here is whatever the order induced by the lattice is. Now we can use Khan extensions to give a canonical semantics is, well, this is my claim. I might be proven wrong in 2 to 10 years. But this is what I think is the canonical semantics for intuitionist modal logic. Suppose you have a Kripke frame, so just a set with an order. A relation on W, an endo relation, is a bimodule just if it can absorb increase of information on the right and decrease of information on the left. So if W is related to V, and I can increase V to V prime, and I can decrease my information from W to W prime, then actually W prime and V prime are related already. Equivalently, I can write this relation as a function, a monotone function from W op and W into 2. If you write out what it means for this function to be monotone, you'll find exactly this condition. If I lambda abstract this, I end up with a function big lambda R from W op into W2. So the monotone functions from W to 2, also the upper sets isomorphically. If now I take the Khan extension of this along the Unada embedding, which now goes into covariant upper sets, so upper sets, I get a joint preserving map, and this has a right adjoint. And if you write out what these maps are, they are exactly what you would expect the modalities to look like. So the right one is exactly what the box modality would be in traditional modal logic. The left one, the diamond, looks a bit different. So if you have a set S, which are the worlds where something is true, diamond of S gives you all the worlds such that there exists a V, which is related to W, and V, S was true at V, S now being a predicate. So it's the opposite variance. If you know modal logic, it's the opposite variance to what you would have been used to. That's why I write black diamond instead of white diamond. And in particular, every such adjunction on upper sets, look, this is an adjunction, an endo adjunction, as Steve said, corresponds precisely to bimodule. Why? If I have either the left or the right adjoint, they uniquely determine each other because these are both complete lattices. And if I have it, I can precompose the principal upper set or Unada embedding. I can get a morphism of this type. And this morphism by Cartesian closure will be exactly a bimodule, a monotone function. So this is an exact equivalence. So if you have an endo bimodule on a set, you get a prime algebraic lattice with an operator on it. And which one you pick is immaterial. If you have the diamond, then that preserves joins, so it has a unique right adjoint. If you have the box, then that preserves all meets, so it has a unique left adjoint. So all these three presentations are equivalent data. A bimodule, the black diamond, something that preserves all joins, or the white box, something that preserves all meets. And this gives us the duality between endo bimodules and prime algebraic lattices with operations. Let's look at the logic that arises from this. It's a very simple tense logic, as you would call it. One modality, the black one, can be considered as in the past phi was true, and the box can be considered as in the future phi will be true. W forces the black diamond of phi exactly when I said, which is if there exists a V from which we can access the current world W, and V forces phi. And correspondingly, when does W force box phi? Exactly when for all accessible worlds from W, so accessible from W related to W by R, then we have that V forces phi. The logic looks a bit like this. If you have an implication and you have a black diamond in the antecedent, you can move it to the consequent. And if you have a box on the consequent, you can move it to the antecedent, it becomes a black diamond. And these are exactly the rules that you're used to for an adjunction. And then because these are adjoints, they preserve, the left one preserves all joins, the right one preserves all meets. So you get all the usual rules you'd expect. So boxes distribute over implications. If phi is true with no assumptions, then box phi is true. Box true is always true. If diamond false is true, then actually we're proven false. And black diamond also distributes over implications. Now, the usual white diamond is not monotonic in this setting. So if you try and plug a white diamond here and you reverse the order of this relation, you'll see that the monotonicity is no longer true. So if information increases at W, I can't absorb it here. Whereas the way it is now, if I increase W to W prime, I can increase it there. And by the bimodule, I can absorb it into the relation and have that this fact is also true at W prime. But the usual white diamond is not monotonic, which is one explanation of why the white diamond is not really compatible with intuitionistic logic. Many ways to go around this have been developed, but none of them completely satisfactory, at least so far. Okay, it is very easy to categorify this and lift it to categories. Bimodules just become profunctors, essentially a relation on a category, which for two worlds gives you a set of proofs that these worlds are related. The fact this is a functor is exactly the bimodule condition. You use the left Kahn extension along the Yoneda embedding, and you get an equivalent, similar to duality. If you look at the modalities and pre-sheaves, they look exactly like what they did in the previous slide, but now they carry proofs. So if P is a formula, diamond P is another formula, what proofs does it have at W? Well, you can read this coend as an existential. You need a V such that P is true at V, and I have a way to access W from V. And correspondingly, the white diamond gives you an end, so that's a bit more like a limit. It says for all V's that are accessible, I have a proof of V. And hence you obtain a theorem, if you can call it a theorem, because it's extremely well known, that a two-dimensional Kripke semantics over C uniquely corresponds to an adjunction on the category of pre-sheaves on C. Okay, so this is the big picture. Surprisingly, if you look at the literature, the first thesis on this was by Vladimir Sotirov in the late 70s, and he'd figured most of these things out. Somehow we forgot most of them, and now we're rediscovering them. But so far, everything is known. In the last part of the talk, I want to talk a bit more about what you can do with this kind of perspective and how you can incorporate categorical thinking in the semantics of modal logic in particular. So there is an argument here about the completeness of these semantics. It is well known that both Kripke semantics and algebraic semantics are complete. And this means slightly different things. But in the case of the algebraic semantics or the categorical semantics, you simply construct a lattice or category out of the syntax. And then you say if it's true in all Heyting algebras or Cartesian closed or bicartesian closed categories, then it's true in the one made of syntax. Therefore, it's provable. In the case of Kripke semantics, you have to do a bit more. And there are interesting connections there with reverse mathematics, because the completeness of Kripke semantics depends on various slightly non-constructive principles. Okay, so the first three lines exactly say what I just said out loud, which you could call relative completeness. Suppose the formula is true in all Heyting algebras, then it is true in all prime algebraic lattices. Why? Because every prime algebraic lattice is a Heyting algebra. Therefore, it is true in all Kripke semantics. There's a little theorem you can show that connects truth in the prime algebraic lattice to truth in the Kripke semantics. So in some sense, the algebraic semantics is as complete as the Kripke semantics. If you know that the Kripke semantics is complete, this argument gives you that the algebraic semantics is also complete. This time not by Lindenbaum-Tarski, but through the other result of Kripke semantics. You can also have an argument in the opposite direction. There's a classic proof that whose origins are lost in the mists of time, but I found it in a book by Fitting, the earliest occurrence I could find in the 60s. You can read a nice description of it in the recent paper book by Mai Gerke and Sam van Gool, which was published last year. And the trick there is to make a Kripke frame made from prime filters of an algebra. So this prime thing is the non-constructive bit. And then you can have a similar argument to the above, which shows another kind of relative completeness. And then you can prove that the Kripke semantics is complete from the completeness of the algebraic semantics, which is the most general and easier to prove complete. For this logic, it has been done in the paper that introduced it, the Zick, Järvinen, and Kondo, 2010. It's in section 5. You can have a look at it. But it's also not constructive, and it's not very nice. Nice is used in a technical way, which means we can't immediately categorize that, because how do you have a prime filter? I don't know. Maybe someone in the audience knows. I'd be happy to hear about it. So there are no real nice ways out of this, but to just change what it means to have a Kripke semantics. And this is what I will just do now. So I will introduce the stable semantics of intuitionistic logic. Before, we had a set of worlds and we had an order on it. Now we'll replace that with still a poset of worlds, but now this poset, W and the order, will be a distributive lattice. So we'll have and or now on the worlds. And you can think of that as taking the meat of the information in the worlds or the join of the information in the worlds. And how did we go to Heiting algebra? We had upper sets. Now we'll do something else. We'll take filters. A filter, this is the definition that works for a distributive lattice, is a set of worlds which contains the top world. And if it contains two worlds, then it contains their meat. So if X is in F and Y is in F, then X and Y is in F. And then I can play the same game by defining a relational Kripke style semantics over this. When is a proposition true? Well, exactly when it's true. If I assign to each propositional variable a filter, then W must be in that filter. When is false true? When does W false false? Actually, it will sometimes, exactly when W is 1, the top element of this distributive lattice. I've written it as 1 is less than W, but W is of course less than 1. So by antisymmetry, W is 1, but I've written it this way. The reason will become clear in a couple of slides. Conjunction is as before. Implication is as before, but disjunction I shall change. And when will W force a disjunction? So phi or psi is true when there exist two worlds, V1 and V2. V1 forces phi, V2 forces psi. And moreover, if I take the joint information in these worlds, it is less than the information I currently have. So there are two possible futures that force both of my disjuncts, and the information common to these disjuncts is actually compatible with what I have now. So it's below my current world. These two will eventually become closely related, but the idea is that one is a place, is a world which forces so much information that it makes all formulae true. Actually, you can prove that one forces every formula in the semantics. And I will show to you very quickly in the next slide or two that this is sounded complete for intuitionistic logic. I've never seen this written down. It looks a lot like Beth semantics. I've asked people around. If you know the reference where this appears, I'd be extremely happy to hear about it. And that was a spatial semantics. So we can now play the same trick and end up with an algebraic construction. So let's start with a distributive lattice, as we did, and take 2 again. We'll take maps, monotone maps from W to 2, but this time they won't just be monotone, they'll also preserve meets. Let's look at what these look like. Actually, each one of these maps is exactly a filter on W, with the order being inclusion. It is, again, a complete Heiting algebra. It has arbitrary joins and meets and an appropriate distributivity law, which make it a Heiting algebra. So I can interpret all of intuitionistic logic in this order of filters. For each W, I have a principal filter. It's defined exactly as before, but now it has extra properties. This map preserves finite meets, finite joins in addition to meets, and exponentials. Therefore, if I take a Heiting algebra, H, I can embed it into the filters over it. But the filters over its opposite, not H itself. So I take H op, I take filters, which in this case would be ideals, I suppose. And then I end up with an embedding of any Heiting algebra in such a contraption. Similarly, an element of this kind of thing is compact. So it's less than, well, here we have directed joins. So it's less than a directed join if there exists something in the directed set X, which is below it. And such compact elements are exactly the things in the image of the principal filter embedding. And finally, every filter F is a directed least upper bound of compact ones. So every filter can be written as the join of, well, you take all the things in F, you take the principal filter, and this set is directed, and then you take the directed join of these things. And in short, you can say that W2, pardon, there's an and missing down there, so the typo, is a spectral locale, as we know from stone duality, or if you look at the opposite category, a coherent frame. That's what Johnston would say in the book. So that's an algebraic complete Heiting algebra whose compact elements form a sublattice. Okay, so what's the benefit of doing all this? The construction looks very similar to what we did with prime algebraic lattices. You also get a duality, and completeness is maintained. There's a principal embedding. Primality is replaced by compactness, and the upper set being a join of primes below it is now a directed supremum of compact elements of the filter. So there's a very close correspondence to what we're doing here. It seems almost the same. And we get a duality once more. And we have that the category of distributive lattices and meet-preserving maps, which I call stable here, maybe not the best terminology. I'm open to changing it. If you take the opposite of that, you see the category of coherent frames and Scott continuous meet-preserving maps. Mind you, this is not the usual category from stone duality because the morphism is slightly different. But we get that the stable semantics and the Heiting algebra semantics are equicomplete, and this is constructive. Why? Because if I start with a distributive lattice, I can make a Heiting algebra. If I start with a Heiting algebra, I can see it as a distributive lattice and embed it in such a canonical construction, a spectral locale. And I'm not going to go into it due to lack of time, but all the previous work on modalities carries through nearly verbatim. And I have a map from any Cartesian closed category with an adjunction, well, by Cartesian closed category, into an appropriate thing that preserves all the logical constructions, so and, or, an implication. Okay, now what's the correct categorification? All of what I did so far is just order theoretic. Now I want to take it up to categories. There are at least two ways to mimic filters over a category. And one is to take the int completion, and the other one is to take the sind completion. For various reasons that I go into in the paper, I will choose the sind completion. So how does that work? The sind completion adds all sifted colimits. And this is a construction that's extremely well known from Lorvier theories. It's the way you go from a theory to this category of algebras. So if you let C be a category which has finite products and coproducts and is moreover co-distributive. So this is going to be slightly odd to most people. It says that products distribute over sums. It's the opposite of what you'd expect, or rather the op is a distributive category. Now, a two-dimensional stable semantics will be exactly semantics of proofs in the category of algebras over such a co-distributive theory. So this category C with finite products and coproducts can be thought of as an algebraic theory in the style of Lorvier. If I take the product-preserving presheaves, that's exactly the category of algebras over this theory. So to each sort, you assign a set, preserving products, and also acting really nicely on morphisms. And that is exactly the same as the sind completion, the sifted colimit completion of the opposite category. And it's a not too well-known fact that if C is co-distributive, then this category of product-preserving presheaves on C is Cartesian closed, and actually vice versa. So if this category is Cartesian closed, then C is co-distributive. You'll normally see this in the distributive version. So C is distributive if and only if C op into set product preserving is Cartesian closed. This is a factor to Marcello Fiore from one of the axiomatic domain theory papers in the late 90s. And for any bicartesian closed category, we have that the Yoneda embedding is an inclusion into these product preserving presheaves and preserves products, co-products, and exponentials. We get a fact for free from this, and I didn't promise, but here's a theorem that we have. The category of product preserving presheaves over codistributive C is actually a category of possible models of type lambda calculus with sums, and it is complete. And completeness here is in the sense of the interpretation of proofs. So if a lambda term is mapped to, if two lambda terms are mapped to the same proof in all possible models, then actually that was provable in the equational theory. So that's most of what I had. It was a quick overview of things that have happened. I think there is a lot more to this research program. So a number of things that you can think about are to imitate axioms of modal logic. So for example, the most canonical modal logic is S4, which additionally has a relation that's reflexive and transitive. Now, there's an old theorem, excuse me if I go back a little bit, there's an old theorem from about the late 2000s by Asada, which says that if this profunctor is actually reflexive and transitive, so essentially if it is an arrow in a particular sense, then this left-hand joint induced by the Kahn extension is a monad. And for purely formal reasons, the right-hand joint is then a comonad. So this does extend to S4. It's not clear to me that this relates somehow to algebraic effects, because this will have to preserve all joints. So the induced monad is not so nice. It's maybe a very restricted kind of effectual thing. There's also a version of these dualities that targets relations. So if you look at the category of relations, of course, its opposite is the category of relations, but you can also express it through the Pauser construction. You can go to categories of complete atomic Boolean algebras and equivalent relations. And these I'm trying to currently fit into a double category in a way that obtains a double duality. But I think I will stop here, and I'd rather take more questions rather than continue discussing future directions.
Great. Thank you, Alex. So
Thanks,
if people have questions, feel free to press the react button and unmute. Great. Yeah. Let's see. Sorry, I saw a chat, but it was not a question. Oh, Steve has his hand up. So go ahead, Steve.
Okay, thanks. Thanks, Alex. That was a great talk. Really exciting. I'm very happy to see that work. I'm very interested in this stuff. I've been something that didn't come up. I wonder if you have something to say about it. Is a theorem that I've been studying for some years and I'm excited about too, is Joyal's embedding theorem for hiding algebras, where you embed a hiding algebra into essentially the stone space or the prime ideals ordered by downward inclusion, say, and you take the downsets in there. Are you familiar with that result?
If I recall well, that's the theorem in the book by Mackay and Regis, isn't it?
Yes, that's right.
The completeness theorem. Yes, I'm very fascinated by that theorem as well. And I'm not sure I've completely figured out the connection.
Exactly.
What I have understood is that at least because that theorem does work on a truth value level more than a proof level, there is something non-constructive about it.
Yeah, of course. It uses the Boolean prime ideal theorem a couple of times. In fact, the proof uses or the axiom of choice or whatever, uses it twice. Once to show that the embedding is indeed an embedding, that it's faithful, and then it uses it again to show that the exponentials are preserved for the hiding algebra.
So there are some subtle points here. I think this is not announced, but Dominic Kirst and Yannick Foster have been working on completeness proofs in type theory for first order logic. And they have shown, I think Dominic has shown that for intuitionistic propositional logic,
Yeah.
the completeness is actually equivalent to an indexed form of lem. So if you have a predicate over natural numbers going into prop, then it must be that for all n, either P of n is true or not P of n is true. So there's something highly non-classical going on there that I can't quite get my head around.
Okay.
I don't think this has been announced, though. So please don't take my word for it. Ask Dominic.
Right.
Do you have a draft of that theorem in your book draft?
That's right. It's not only for the propositional case, but also for the predicate logical case.
Yeah.
It's in there. I don't prove the predicate logical embedding, which says that every Heiting category, not poset, every Heiting category embeds as a Heiting category into pre-sheaves on a poset, not sheaves. So the Kripke semantics that I'm interested in, it has pointwise joins, right? Not sheafy joins like what you're doing in your semantics. And the pointwise joins in the pre-sheaves, I think, is a simpler Kripke semantics. We know it's true from Kripke's theorem that you can do it, but we don't have a categorical proof of it. And the categorical proofs all use prime elements or sheaves or something. But the proof of Joyal does give a categorical proof of the embedding for a Heiting category into a category of pre-sheaves. Indeed, you can do pre-sheaves on a poset. And recently, a visiting student from Lucerne wrote a master's thesis with Mathieu Anel and me here at CMU. And there's a link to it on my website. Her name was Julia Morin, and she gives a categorical proof of Joyal's embedding theorem for Heiting categories. And I conjecture, I think probably it's true, that you can do the same for bi-CCCs. You can embed them into pre-sheaves in the same way.
So that'd be very interesting to look at.
Yeah, that's what I have to say.
But there seems to be that if you truncate, something becomes non-constructive.
Oh, I think so. Yeah, I think the whole thing is non-constructive. The embedding, even for first order logic, it's essentially Gödel's completeness or Deligne's theorem. It's non-constructive.
Yeah, so for me, an important design criteria in this work was to remain as completely constructive as possible, in particular because I'm interested in models of modal type theory. And indeed, the study here does extend to what you could call dependent right adjoints.
Yeah.
So if you have a particular profunctor, then you, by Kahn extension, you induce the adjunction, and then the right adjoint has a particular DRA structure.
Yeah.
I will write this down at some point. I just haven't had the time.
Yeah.
But yeah, a lot of people have been working on normalization by evaluation for modal type theories.
Yeah.
And if you look in particular, when these people are not category theory minded, they do it in AGDA, it's proof relevant, and they say, look, completeness for Kripke semantics is just NBE. But the truth is, it is proof relevant. They have used something a bit more than what you'd have in a categorical logic setting. I think this mismatch is really exciting.
Thanks for those comments. Yeah, very interesting talk. Thanks.
Great. Thank you, Steve.
Yep.
And Valeria has her hand up.
Yeah, thanks, Alex. It's good to see it kind of coming up like that. My question is very different from Steve's. It's much more on the. You see, I think my desiderata criterion are very much more like Alex's than yours, right? I kind of wanted to know what can you say about K modal logics and stuff like that, the variants of because I kind of tend to believe that the philosophical logicians have a point when they've been kind of putting so much more weight on other things, and and in particular, I think if you go back a little bit more to this little bit of natural deduction or of logical rules that you have at some stage.
Yep, hang on there.
There. I mean, I think that looks very strange to me in some ways, right?
Yeah.
In particular, in particular, I hate the idea of the diamond falsum implies falsum, because of course falsum implies diamond falsum. So possible falsum is exactly the same thing as falsum, right? You know, that is a hard one to swallow for me.
I agree with you. It's the same for me. Okay, here's some things I've figured out. I'm going to say them in no particular order. If you suppose, okay, so here's the bimodular extension slide. If you suppose W is just a set, right? It's a partial order with the identity relation on it. If you do this construction, you still get something. This thing is the power set, and this thing is the power set, and this is the modality you expect, and this is this odd thing that we have here, okay, which goes in the wrong direction.
Right.
If you look at traditional books on modal logic, this map is everywhere. So they call it a completely additive map. So in even classical modal logic, this adjunction is implicit everywhere. They just don't talk about it.
Right.
That's observation number one. Observation number two, you don't need to have this in your logic. It's there, but you don't need to have it, is the answer. So you could just drop this connective and this Falsing criterion. The black diamond, however, if you look at these Fitch-style natural reduction systems, appears as a lock on contexts. And then you have the traditional rule that says a locked gamma proving A implies that gamma proves box A. So the lock appears as an operation of contexts. If you write it in the way that a classic computer science book, like the book by Huth and Ryan, would write it, it appears as opening a box. And if you, even if you read philosophical logician books when they do Fitch style, it's, if you linearize that notation, it's exactly just the lock. So implicitly, even in the Kripke Semantics, in the book by Blackburn et al., the completely additive maps are there. And even if you just have box in your logic, the lock is probably still there secretly. So there are certain patterns here that keep reappearing.
Right. But, you know, the fact that the lock is there doesn't help me much, because I have kind of qualms against Fitch semantics by itself, because we don't have very good notions of normalization in Fitch semantics. We don't have the Kravitz notions of kind of, you know, normalization doesn't come naturally on that, right? So
there has been some work on that, so the situation is somewhat improved. But there are various syntactic issues. We had a paper at Topos with Daniel Greitzer and many other authors on parametric right adjoints, which seems to be the correct structure to get everything working really, really nicely with Fitch. And if you have a parametric right, if your box is a parametric right adjoint, if your diamond is a parametric right adjoint, so there's a further left adjoint, a lot of the syntax works really, really nicely. And actually, if you do type theory over it, it becomes all sorts of other things like ticks in guarded type theory or dimensions in cubical type theory. So there are still things to look at there. The simply typed case has not been looked at carefully. I think it deserves to be done at some point. I think there must be easy conditions on the profunctor, so on the bimodule, to guarantee that condition, but I haven't worked them out yet.
Well,
But
I'm sorry, carry on.
Yeah, frankly, just as a concluding sentence, the more I work on modal logic, the less I feel I know.
Right. Well, you're not alone on that feeling. Thank you so much.
Thank you, Valeria. Alex, I don't really understand a lot of the implications of this, but it seems like you went from Boolean enriched categories and Boolean enriched profunctors, which is what some people call co-design. I mean, the only reason to call it that is because it has implications or applications to design. But that's what they studied there, is these Boolean enriched profunctors. And then you kind of upgraded to set enriched profunctors. But does your whatever you've done here, does it work for any V enriched profunctors? Like, would you have a version or?
My enriched categorical theory is not very good yet, but my answer would be probably yes, as long as V is nice enough. So if it's a particular kind of cosmos with good colimits, you should be able to do all this stuff.
Cool. Nice. So you could do this for metric spaces, for example, if you use that cost category instead of the Booleans. Cool.
Exactly.
Okay.
And you would get some kind of enriched logic in the sense of Lorvier. Yeah.
And would the numbers, like where would it be over the turns? Where would those, say, the proofs or the numbers in a metric space, the distances between things, would they occur over a turnstile, or how would you see them in the logic?
That's a very good question. I don't know the answer to that. You could possibly, maybe the parametric right adjoints have an answer for that, but I don't know. That's an exciting dimension. Thank you.
Cool. Sure. And on that note, I guess we'll end the live stream. So, and as a lot of people know, we often stay later and talk off the record. So if anybody wants to, oh, sorry, I should have thanked you again, Alex.